In this slide, we will check an example to write a pseudocode for an algorithm for roots of a quadratic equation. So basically, if we have a quadratic equation, as you can see here, we simply find the roots of this equation. There are two roots because it's in second order. We can use this formulation, as you know from calculus, to find the roots of this equation. And we want to develop an algorithm that does the following. Step 1, which prompts the user for the coefficients a, b, and c. So basically these coefficients, we will just type these down first. In the step 2, we will implement the quadratic formula, guarding against all eventualities, for example, avoiding division by 0 here, and allowing for complex roots. We need to consider these, but this is actually, we can ignore this first. We can just start with step 1 to go to step 3. Display the solution by calculating this. That is the values of for x, we find these. And then it allows the user the option to return this to step 1 and repeat the process. So we can have step 1, step 2 with implementation, step 3 and 4, or also we can have an advanced code or algorithm with consideration of avoiding division by 0 and allowing for complex roots, because these can exist in some cases. So let's try to solve this in the following slides. So here is the solution for the quadratic root finding example. The pseudocode for the simplified version for this example is that we start with inputting a, b, and c in a for loop, or do and undo loop actually, with the condition of try again, yes or no. We calculate two roots with the formulation as we wrote here for this formulation, and we display the results. And if we want to try again, we answer yes, or if we don't want to, we just answer no. And if it is yes, we continue. If it is no, we exit, and that means we finish with the calculation. And if it is yes, it goes to the beginning, calculates again, and continues. So this is the simplified version, and there are two issues with this. First of all, if a equals 0, because it is a denominator, if it is 0, there is a division by 0, which means it's a problem. Close inspection of this equation indicates that two different cases can arise. If b equals not 0, so a is 0 and b is not 0, then there is a linear equation with one real root, c divided by b. So we can just define this. And if b is also 0, if this is also 0, everything is 0, no solution exists, that is, the problem is trivial. So we can improve this pseudocode, the blue part. Over here you can see we actually improved it, and we defined R1 and R2, which are the two roots, as 0 in the beginning, and we also have some increments, I1 0, I2 0. Then if we have an if statement, if a is 0, because here we will consider about this condition, then there are two conditions, b equals not 0, then R1 is minus c divided by b over here. Else display trivial solution, because if b is 0, then no solution exists, it's a trivial solution. And we finish this first condition with this. Another condition with else is if a equals not 0. So here if a equals 0, we said that there is an if here. The other conditions are a is not 0, then we can use else basically, which means if a equals not 0. So here we will have two possible cases, and we will actually a calculation of d, b squared minus 4ac. This one is d over here, and we can simply calculate this. As you can see, this discriminant, or this one, b squared minus 4ac. Then if d is greater than 0, two real roots occur. If this is greater than 0, then R1 and R2 simply be calculated by this equation, because there are two real roots. But if it is smaller than 0, then complex roots exist. Then we need to identify this. Else, which means this discriminant value is smaller than 0, then R1 is minus b divided by 2 times a, and R2 is R1. Also there is I1 and I2. These are the complex root components. And with these we can again show R1 and R2 with the I values, which are the complex root values, and we can show these. And if we want to try again, we can try again. This part is the same, just generic, but the blue part was improved to include these conditions to be able to have a more robust solution to find the roots of a function. Here I will show another example for developing a pseudocode for making an algorithm, and this is for the parachutist problem that we solved in the chapter 1 videos or course classes. And let's remember that given an initial condition for time and velocity, the problem involved iteratively solving the formula, the Euler's method. And if you remember the numerical formulation for the parachutist problem, we have the v at I plus 1 equals vi dy divided by dt and delta t. So this was time step size, this was the slope, and this was the initial velocity. And in here, dv divided by dt was g minus c over m times v. And we want to just simply develop a computer code to be able to calculate these iteratively for each time. And a simple pseudocode for this is that we type in g value, input cd and m. These can be constant, but can be different, so we just define them as inputs. And also input ti, vi, the initial ones, tf, and dt. Tf is the final time, dt is the time step. So time change, let's say. So t is ti, v is vi. So initially these are the t and v values. Then we will have an n count value, so we will use do for with a count number. So with the final and initial time difference divided by the increment of time, like we define for example in chapter 1 2 seconds. So we can divide by that, and we can have an n number. So we continue calculation until this I reaches to n value, so from 1 to n. And we will have a function dv dt, which is actually this one, which calculates dv dt value based on these inputs. We will have these. Then we will calculate the next v, as you can see here, by using this formulation, v plus dv dt times dt. And we need to also calculate the next time, which is the first time plus dt, the increase of time. And this finishes, and if I is not n, the calculations continues, and if I is n, then it stops and it shows all v values as display v. So this algorithm will work only if the computation interval is evenly divisible by the time step. So which means that the difference of tf and ti should be divided by dt, and we should have an integer number as the n value so that we can continue from 1 to n. But if it is not divisible, then it's a problem. To cover such cases, to eliminate that problem, a decision loop should be substituted in place of shaded area, or in this blue area in the previous pseudocode. What we do is here that we actually define an h equals dt value, and if we have, for this division, if we have a condition, if t plus dt greater than tf, then h is tf minus t, and we finish this statement, and then we calculate all the others. And here we have dv dt times h, so because we define h. So with this h value, it will be easy to be able to have to solve the problem of evenly divisible, if there is no evenly divisible n or dt value.